Okay, let's continue this elementary introduction into duality, in term theory duality. So our final goal for today would be the following. Let me explain. In the year 1984, 40 years from now, and actually in these days, happened what is called Spring Revolution. And in the Spring Revolution, people say, look, there is EA times EA heterotic string and if in D equals 10, and when we compactify it on Calabi-Yau, okay, we will get n equals 1 supergravity plus some gauge group plus, and this is important, chiral metric. So what do I mean by chiral metric? I mean that the gauge group would contain representations that are not conjugate to each other, that are not self-conjugate. And in this way, we can form chiral multiplets in D equals 4. Like you know, we have in real world SU2 times U1. And we have say leptons are in representation they are in chiral representation with respect to this group.
What is chiral representation? Because that's some new term for group theory. Like for SU2 and SU1, we know classification of all representations. Like, can you be more specific? Like chiral, it doesn't sound like a group theory term.
A representation that is not self-conjugate. But I'm not going to talk too much about it. I just, so this is kind of reminiscence from the literature.
Yeah, that sounds like a presentation theory, which is something very, very, very classical and very basic. So we should be able to understand what is stated in the literature in group theory terms. Because for SU2, we know all representations, like they are constructed, I don't know, using Young tables, which are very easy, or just labeling by a single integer number.
So here important thing is this U1. Okay, I'm not going to describe all of this stuff. What I would like to come to in my today's talk is this E8 times E8 heterotic string. So I'll explain how heterotic string appears.
I think there was like a slightly separate argument of similar type that for model building perspective, like we really want n equals 1 supersymmetry in 4 dimensions. While standard like type 2b, type 2a compactifications typically give n equals 2,
Exactly.
which is not very good. And so another argument was that really that was the first kind of good model which naturally gives n equals 1 in 4 dimensions.
You see, actually, if we started, so there are two, so before this revolution, there was also type 1 string theory. With the gauge group SO, I think 16, or maybe SO 32, I don't remember. But these were not good for model building. So people managed to get this E8 times E8 heterotic string. So, so let me tell you where I'm aiming. I want to show the following duality. It will be at the end of today's class. So that heterotic string E8 times E8 compactified on S1 to the 3 is isomorphic to M theory that is 11-dimensional supergravity on K3. And this is kind of remarkable to see how E8 times E8 appears in K3. So now I am formulating the answer. And we should be able to understand that how string appears. String comes as M5 grain wrapped around K3. So if I have 5 grain and I wrap it about K3, I'll get 1 grain. It's a string. So I will need to know the theory on M5. At the moment, we had some questions or problems writing down theory on M5 because it's the most mysterious brain. It is not the brain. In particular, we computed that extension. So when we take, okay, When I say that it's not the brain, I mean the following.
There are no strings in M theory, so we did not take the break.
In D equals 11, we had M2 and M5. But then we compactify by S1. So this goes to D2 brain. And now what happens to M5? And M5 goes to so-called NS5. So we were able to compute its tension. Was M string to the 6 over G string squared. So it's another confirmation that it is not a D brain. So what is it? And we need this NS5 brain in order to understand M5 brain, in order to be able to wrap it over K3. So this is why we are interested in knowing this theory on M5 brain.
How is extension evidence for it not being D brain?
So for D brain tension, always goes like
1 to 2.
1 over T. So for fundamental brain, tension is, for fundamental string, tension was M string without any G. For D brain, tension goes like this, and for an S5 brain, so the question would be, what is the theory on this MS, on this NS5 brain? So it's a very mysterious object. We actually don't know what it is in 11-dimensional supergravity. So how do we know that M2 looks a little bit like D2? At least if there is one M2. We just say that when we compactify S1, this M2 becomes the D2, and we were able to study theory of this D2 brain. That was super Maxwell. Find something about the theory on M2. If we have a single D2 brain. It was the end of the last class. Okay, let me repeat. That we studied super Maxwells. In D equals 3. So it should be a theory on the D2 brain. And found that it has 7 stables plus gauge field. Then you can perform duality transformation here on D equal to 3 spacetimes. And this gauge field went to the eighth scalar.
Periodic scale.
Yes, eighth periodic scale. So that's how we understood the theory on a single M2 braid. So Tomoki will tell you how to describe theory on the stack of M2 braids. But it was a theory on the single M2 braid. Now, we would like to understand theory on M5 braid. So that is on an F braid. In type 2A. So this is our goal. So it should be some six-dimensional theory. It turns out that it is possible to get it, and it's interesting through duality. So how would we do it through duality? Let me remind you that there was a remarkable space called tau naught. That I will now depict like this. And let us try to see the brain spectrum if we study the following systems. Let us study 11-dimensional supergravity, so this was too easy. But let us compactify it on two circles. It will definitely be type 2B supergravity compactified on one circle. So I need to tell you what is type 2B supergravity. Type 2B supergravity is a field theory limit of type 2B strings. What do we know about type 2B supergravity? it has the following fields. So these fields phi, g mu, and b mu are common for all string theories. But it has also field phi tilde, d mu tilde, and c mu mu lambda rho. Okay, I also call it tilde. And there was so-called S-duality that interchanged this field and this field, while metric and this C mu lambda rho were invariant. In particular, we have so-called fundamental strings charged with respect to d mu and also d strings charged with respect to d mu. And under S duality, they were interchanged. In particular, the ratio of tensions of these two strings was a coupling constant, computed from the point of view of the string theory, while this thing was invariant. Now, what's important? Important is that this type 2B theory will also have an S brane. These who were magnetically charged. With respect to d mu or d mu tilde. And it is interesting to study the theory on the word volume of these NS branes. One of these NS branes is a D5 brane. So its world sheet theory is six-dimensional supermaximal. So we may say the same for another, because they are S dual to each other. So NSB 5 braid is also described by 6-dimensional supermass. However, do we get from this any information about M5 braid? No. Because these NS5 braids are not, you see, their origin is kind of so we will come to their origin in a second, okay? But these are NS5 brains of type B, and we are interested in the theory on the M5 brain. And M5 brain is NS of the type A. And we have good reason to think that they are different. So how to study all this? The way to study all this is to try to find a configuration where NS brains of type A would appear. We will use the following duality. Type 2B on the circle is so-called T-dual to type 2A on the dual circle. So let me give you argument why this is true. Argument is like this. When we do T-duality, the dimension of brains are changing. So brain that fills, that is wrapped over the space, is replaced by the brain that is placed. So this explains the strategy that I'm going to do, that I'm going to use. I would like to look for 5 brains that I have here and here.
In the compactified theory, or
In the compactified theory.
that NS5 lives in the non-compactified field, right?
You mean this brain?
Yeah.
But I understand this NS5 brain in non-compactified field. So I'm interested in this NS5 brain that is M5 brain that is not wrapped. So that's what I'm going to do. In particular, I would like to trace the fate of, I would like to compare brains here and here. So, in type 2A, compactified by S1 dual, I have the following. In type 2A, I had the following extended objects. I had so-called D0, D2, D4, D6. So it's in type 2A before compactification. Also, I had fundamental string that was F1, and I also had this mysterious NS brain of type A. So when I compactify on a circle, I have all of these guys plus. So D0 could not wrap on the circle. Plus D2 wrapped, I will call it wrapped S1. Plus D4, that is wrapped on S1. Plus D6, that is wrapped on S1. Plus NSA, that is wrapped on S1. So let me call it WD1 wrapped, WD3, WD5, and WNS.
Are you trying to write down all the possibilities?
However, I missed something. So what I definitely missed is I missed here taub nut that I will definitely have here. And this taub nut would live in dimension so it seems to be that it is tau.6. Sorry. So let me see. Type 2A on S1. S1 is there. So dimension goes down by 4. It is tau naught A 5. Now, let us write the same picture for type 2B, compactified on S1. We will get D1, F1, D3, D5, non-wrapped, plus okay, I will call it wrapped. Wrapped D1, that is something 0. Wrapped F1, wrapped D3, wrapped D5. Plus, I'll have here NS of type B. So before I had this NS of type B, and I'll also have wrapped NS of type B. And now let me see how T-duality is working. In particular, here I have wrapped D1 and it goes to D0. I have wrapped D3 and it goes to D2. I have, say, wrapped D5 and it goes to D4 and so on.
Why is the wrapped NS in a 5 should be a 4?
Wrapped 5 braid.
NS.
Okay, now you see I call it wrapped NS5 braid. So I try to see where would it come? Where would it go? So
it 5 brain before it is wrapped.
Yes. So after it's wrapped, it becomes a 4 braid. So good question. So where this goes? So it's a wrapped NS5 braid. Okay? So it should be a 4 braid. Before I go here, I need to inspect what are, so is it the only 4 braids here? It seems that it is the only 4 braids, right?
No, but what about wrapped D5,
Wrap D5, yes.
which is another program? So there are 2 programs.
Yes. So we need to see them here. So here we see this wrapped NS5 brain, and so rep D5 is already here.
Okay. So then that's only four-dimensional object that we work.
So wrapped NS5 brain is the only object. And what about NS5 brain itself? So the object of our main interest. NSA. So this is a 5 brain. Actually here I forgot to say that it's important that we have stalled nut. It's a 5 brain. And this is the object of our interest. Tau nut, statements of tau nut 5 brain under T duality goes to NS 5 brain. Now you say, wow, well, you see from all these dualities, we can see this. If we be more careful, we can also confirm it by computation of tension. So tau nut in type 2b of this one goes to NS5A. Great. Now we are in position to understand what it is. But besides saying this, let us see what can we say about NS5B. So similarly, we can show that NS5B under T duality goes to tau nut in the theory 2A. Let us check easy case where we know the right hand side and the left hand side. So what is tau nut in the theory 2A? We have 10-dimensional supergravity. Here we have 10-dimensional supergravity with the fields metric, B mu, C mu, mu, lambda sigma. So I'm writing and the scalar. Now, let us consider compactification on the tau map. What is important? It's an extra information on the tau nut.
You need compactification with a circle.
On a tau nut. Compactification on this space. It is a geometry. So in this geometry, there is the only two form that has the following property. Let me call it this two form. It is harmonic. And integrable. So being integrable means that this omega 2 wedge omega 2 integral over this space that is R4 is a number. Let me put this number to be 1. How can I use it? So I wrote something crazy. Here I have field C mu lambda in 10-dimensional type A supergravity. And also I had this extra vector. I'm sorry, now it's correct. So how can I use it? I can use it in the following way. So these are fields phi. I can write down field phi as this omega field phi depend on x mu, as omega that depends on y, times the field that I've called phi tilde that depends on xm. Now m is going from 1 to 6.
Wait, once again, phi is the collection of all the fields?
Yes, collection of all the fields. So here, so now I can do, so with the collection of all the fields, I can do this. So where coordinates y will? Coordinates y live here. So we have y1, y2, y3, y4. And we also have x1, x2, etc., x6.
Wait, what, this coordinate space, is it the entire thing four dimension or the base?
So the entire thing is 4 dimensional.
Why did you write R4?
It's a total space.
Is it?
Because its topology is R4.
Okay. Uh-huh. Yeah, yeah.
And the base space here is R3. So I consider decomposition like this, plus fields that are not localized at zeros of tau naught. Non-localized. So I will understand these fields corresponding to degrees of freedom away from tau naught. And these with omega are the only fields that are localized.
Why is it important that this omega is integrable with?
Because I'm writing down the composition of the field phi. And I decompose it into something. And I can decompose it like this. So in some sense, this omega is like bound state in quantum mechanics. So in quantum mechanics, you say psi is psi bound state plus psi of x.
Times.
In ordinary quantum mechanics, you see here I use psi, okay, not this psi.
But here x and y are at different directions, and you say that in one direction it's a bound state, and in the other direction it's...
Okay, so these are not bound in y.
Okay.
Y has non-compact direction, but there is also a direction. Yes, so y has non-compact direction. And what corresponds to this non-compact directions? Degrees of freedom that are not localized. Why here we have degrees of freedom that are localized. So now we can see what is the theory of localized degrees of freedom. So field B mu nu would go,
But phi tilde is, we don't say anything about it. It's not localized, it's...
phi tilde, you see, phi tilde is in direction perpendicular to tau.
And it can be...
Yes. So geometry is like this.
Wait, the other direction is just R6, right?
Yes, R6. So the field C mu nu lambda would be omega mu nu of y times A lambda of x. So from the field C, we have a gauge field. And from the field B, we have a scalar. So here, I'll put attention on appearance of the field A. I'm not going to count scalars, but this field A is just exactly the gauge field appearing in supermaximum.
Wait,
As we expected.
there's something weird here. Like on the left hand side, C, mu, mu, lambda, mu, and lambda all take values from 1 to 10.
Okay,
Omega mu is a,
okay.
no. Omega mu.
C mu mu lambda. So let me distinguish components. This would be with tilde, and here I will put mn.
Wait, so in the 6-dimensional direction.
So this mn go from 1 to 4, while lambda tilde.
Let's call them something else because you already used xm, where m went from 1 to 6. So maybe
I call it xm. Okay, I'm sorry for this abuse of notation. Then it is am here. Let it be this way. So I have C mu lambda m.
these mu and lambda are from 1 to 4.
Yes. And here, this mu lambda are from 1 to 4.
So we didn't say anything about the other components of C, right?
Right, because I cannot get C nu mn epsilon, because there is no harmonic one form. But my main test is I know how to get a gauge field.
By the way, this two form on R4, that is harmonic integrable, is it something famous? Should we
Yes,
know? Should we
just-
know this?
Yes, this harmonic form is just a curvature. Okay, sorry. Mm. This four-dimensional space is scalar space. And this solution is, in some sense, self-dual. So, okay, of course it's famous. But I'm not going to go into these details here.
And it exists just on R4.
Yes.
It doesn't matter how we represent it.
But it exists. So it exists on R4. Okay. You see, when I write it like this, you would say, look. So this omega 2 equals to star of this omega. So there are many two forms that you can write on R4, okay? But what is specific about this is that Laplacian applied to this omega 2 is 0. Laplacian in tau-Black method. And this is interesting. And that's why, and here we have a mechanism of getting a vector field. It comes from the 3 form. Well, 3 form is this omega times the 1 form. And moreover, let us check what happens if we have not only one tau knot. What happens if we have several tau knots?
Wait, the question remains the same. For A, we only get 6 of its 10 components.
6 of 10 components of what?
Of A. A, n runs from 1 to 6.
Of course, because it's a vector field on the brane. It's not a vector field in the full space.
Ah.
It's a vector field on the brane. And once again, suppose I have several tau knots together. Each tau knot gives rise to the form a nu that I'll call I. So in this case I have n capital Maxwell fields. You see, I am just confirming prediction that I did. So previously I told you that this is a deep brain and there is an axiom. The theory on the deep brain is a supermaximum. Now I'm going through dualities and I confirm this prediction. So it is always possible to see which axioms I'm using. I kind of underline them. As an axiom, I used the relation between is an axiom. Okay, let me rewrite the list of axioms. Deep brains and D-duality. Second axiom is that 11 sugra plus M2 plus M5 compactified on S1 is type 2A superscript. I use the axiom number 3, that is the world volume theory on a deep brain is supermaximum. And I can test compatibility of this axiom. I see that they are compatible. And from this, you see, I made what I did. I just made a check. I made a check that really, if you compactify on tau naught, theory of type 2A, you are getting the theory on tau naught. So that is gauge theory, and then I use this T-duality, saying that, well, if it's like this, then I know the tau naught in the B. Sorry, then I know NS. Then I know NS brain in the B theory. And it is exactly as tau naught theory in the A theory. So it fits. I get supermaximum. And now I'm coming to the last point in this consideration. So what would be if I will apply this here? Tau naught into B should go to NS 5 brain in A. And this is the question that we were making. this elusive field. So what should I do? I should study type 2b supergravity, so what is known about type 2b supergravity? It's what is known as its field content.
Sorry to interrupt. Are we going to make a break or are we going to finish?
I think we, so I think we, let me see. When did we start and what time is it now?
We've been going for an hour and 10 minutes.
Maybe we will go, okay? So I have here the following fields. Two scalars that I don't care too much. Two fields, so I already wrote them down. And then the field C mu lambda sigma. And what is known, and this is known from type 2b supergravity, that this C is self-dual. In which sense it is self-dual? First, it is impossible to write Lagrangian for type 2b supergravity. Only equations of motion. Second,
Is there a metric?
yes, of course, metric. Only equations of motion. Second, among the equation of motion, there is equation for C field. It is dC equals star dC. It is called self-duality equation. So now we will study Taub-Nat in type 2b and see what is this elusive theory of NS brains, of NS5 brains in type A theory. Now answer is simple. C mu lambda rho is omega mu. Okay. C lambda rho mu mm is omega in the same notation. Lambda rho and some field that I will call B small and that. So this field is a two-fold. equations dc equals star dc lead to equations dB equals star dB. So this is the cell duality equations in 6th dimension. So we finally got this elusive theory on NS5 brain. It turns out that it is a theory of two forms with self-duality and corresponding number of scalars. That's why it is not like theory on the D brain. That's why it is that different. Now, the question is it possible to work with self-dual theory? And interestingly, the answer is that we can understand this self-dual theory somehow. Self-dual theories. First of all, self-dual theories happen in dimension equal to k. And here equations of motion were dc equals star dc. However, it's interesting that while it is very hard to imagine what is going in d equals to k, we can still understand self-dual theories compactified on S1. Suppose that here I have coordinates y1, y2k. Let me make a compactification and let me say that y2k is compact. Then from C, mu 1, mu k, I am getting two fields. C mu 1, mu k minus 1, and here I put index to k, and also C mu 1, etc. mu k. So k form gives me k minus 1 form and k form. In dimension that is 2k minus 1. And equations of motion for the C field dc equals star dc lead just to dc k equals star dc k minus 1.
Can you clarify again, how do you go from K form, so to K form to the, what's the right hand? C mu1 mu k minus 1 mu to k.
No, well, and here
Just
has
to-
index to k.
To k.
So here is 2k and here is 2k.
Yeah. How do you go? How do you open?
I just say that the last index is 2k.
Okay, sure. You just said it.
And then mysterious equation of motion take very standard form that I could get from Lagrangian. And this equation are coming from the Lagrangian dck star dck. Let us check it. Equations of motion here are written in the form d star of dck equals to 0, right? So it's exactly to say that dck belongs to the image of d star.
Why? It belongs to kernel.
Okay, it belongs to kernel of d star. However, if I'm on the flat space, the kernel of d star and the image of d star is the same. So on the flat space, I will say, look, from this equation, I say that there is some ck minus 1 such that it happens. So that's why compactification of the self-dual theory is not that terrible. It has Lagrangian description. However, uncompactified theory does not. And this explains how it happens. This explains why sugra of type 2A on S1 could be isomorphic to sugra of type 2B on S1. Here we do have this self-dual field. Here we do not. But that's not a problem. When you compactify to S1, we will lose these self-dual fields completely. Now, another question is one would ask. This sugra type 2B on S1 dual, what would be if I take R dual to infinity? It would be the compactification. But it would mean that I'm taking the radius here to 0. And many interesting phenomena would happen. So brains could wrap this as well, and I will have non-geometric degrees, non-geometric space-time degrees. Like here I have momenta in S1, and in this duality I will have winding. So you see, at the common level of understanding, the so-called M theory is a set of axioms that do not contradict to each other, but they are not derived from the single principle. So each time we compute using the axioms that I raised, you are getting something reasonable. And maybe here we can make the last test. What would be M11 to 11-dimensional supergraph on tau gnat? We expected this to be a D6 brain. Okay? Actually, 11-dimensional Sugra has C mu lambda field, and we are getting actually a gauge field for a D6 brane. So what I did? I made a confirmation of axiom. So I had some axiom that the action on D brane is a supramaximum. And now I have these dualities. I can check this axiom. Would I get contradiction out of it? And I have another axiom. And another axiom is that M theory, that elementary supergravity compactified on a circle is type 2A string. I'm sorry, type 2A string. And I'm looking for contradictions. I'm not getting that. So last time we checked tensions. Here I can even check field content of the theory. Yes, compactifying on the tau knot actually gives me D6 brane not only from tensions, but also because C mu lambda gives me omega. C mu m. So I'm not surprised. It works. Okay, I think it's enough for the first half. Yes. And then on the second half, I'll explain something about E8, about K3 manifold, and all that. But now questions.
When you talked about the Lagrangian description of the compactification of the subdual theory, so we got from the equations of motion that dck should be d star of something.
Yes. Or you see, I can put C squared, star squared.
Yeah, I get it. But the original equation that dck is star d of tk minus 1, these ck and ck minus 1 are not independent, they're related. They came from the single object.
Yes. So if you start with a single object and you compactify, you are getting two objects. They are not related because they are different components of the form in the 2k dimensional space.
Yeah, I guess that's right.
So when people play with this, so how people play with this M5 brane? They take M5 brane and then they wrap it around something. And when they wrap it around something, you are getting something with. So in the morning lecture, I kind of explained you what is the theory on M5 brain. That is different from the theory on D brain. And there is no duality that takes it to fundamental string or deep brain. Yes?
If I want to formulate these things in a mathematical language, on what extent does these two structure equivalent? I mean, the singularity to a amplify or something and to be all.
Unfortunately, here we cannot formulate it on a mathematical language. Because what we say is that theories on one background is equivalent to theory on another background. What does it mean? It means that if theory have Lagrangian description, then Lagrangians are equal. If theory has extended objects, there is a matching between extended objects. If extended objects have tensions, then tensions should match. And in principle, one should say that all processes in one theory and all processes in another theory should be equivalent. But we don't know how to formulate in mathematical language the idea that all processes. Because would it be quantum field theory, would it be standard quantum field theory, you would say that there should be a match between correlators, such as correlators in one theory are equivalent to correlators in another theory. Probably we may try to say it here. But then the question would be how to determine all observables that match. We determined only some of observables, like D brains. But there would be other observables. So that's why mathematical formulation of these dualities are far from being understood, very far. So many theorems appear. You compute something on the left-hand side. Duality tells you that there is something on the right-hand side. You compute it on the right-hand side, and wow, results agree. So if statement is easy, it could be computed by physicists. If statement is not that easy, mathematicians are coming and computing what's going on. And they call it conjecture, and they are proving conjecture. But since the structure, the fundamental structure is unknown, it's very hard to prove something here. Because I say, theory contains extended object. What does it mean mathematically? What about other extended objects?
But you mentioned some mathematical things like E8 times E8. What
Okay, it's not mathematical things. You may see it's combinatorical thing. So in the afternoon, I will talk about it, okay? But once again, the actual task for mathematicians is not to be excited about some small piece of mathematics on the left-hand side equals to some small piece of mathematics on the right-hand side. Great. It's not great. The great thing is to understand the structure of the left-hand side and the right-hand side.
I have a question, another question about the procedure. So, can we do something in the opposite direction so that Lagrangian is kind of Maxwell? Can we write, if we have a Maxwell theory in dk minus 1 dimensions, can we formulate it as a field theory in 2k dimensions? Say if we have a three-dimensional electromagnetism.
Of course, you just have to say that in the Maxwell theory, in the opposite direction, you have the following equation on both. Okay? Then you say, look, it means that the DC, you introduce field Ck plus or minus 1, I don't remember, equals and I say, look, this equation could be considered a self-duality in higher dimension.
Would that be useful in some context, or?
I don't know. Because what would be useful is to say that it's not only on the level of zero modes, that it is also true on the level of all modes. So you start with the theory in 2k minus 1 dimension. You conjecture theory in 2k dimensions. But then, interesting thing would be to compactify it on some manifold M, such that this manifold M could not be lifted from compactification of 2k minus 1. So suppose that this M includes 2k's coordinate. And then you say, look, we have diffeomorphism of M. That interchange coordinates. They interchange the, so here we have imaginary 2k's coordinate when we go to 2k. And then we say, look, now we will compactify using the ordinary coordinates here and this imaginary coordinate. And then we say, look, Now let us take diffeomorphisms of this M. That would interchange this imaginary 2K's coordinate with all other coordinates. It's pretty not obvious that it would work.
Again, that is if we kind of mix up the coordinates of this 2K.
Yes?
But in this example, in the forward direction, we only touched this last.
Yes,
direction.
yes, in this example, we were going in the following. 2K compared to phi minus 1 gives 2K minus 1 plus something, plus closed line mode. So if we ignore this closed line mode, we are getting actually 2K minus 1 dimensional stable. But if we are keeping track of this closed line mode, we are getting something more interesting.
How are they supply nodes if we go from an even dimensional theory to one? Because without the Lagrange description, just self-judge. Because in the fluid supply example, we had like electromagnetism in 5
So there are some other fields in the theory that could have this mode. By the way, I still think that we can have this Kausik-Line mode. I don't know at the moment how can we get it.
Okay.
So I don't know how to treat Kausik-Line modes. Okay. So what we have done up to now? Up to now, we have studied compactifications of supergravity on a circle and on Taub-Nernst space. And now I will do the following. I will introduce so-called K3 space. The only non-trivial. I will put it this way. Consider two complex dimensional compact manifolds. So there is a concept of compact manifold with a metric preserving supersymmetry. So compact manifold with a metric preserving supersymmetry is called Calabi-Yau space. In complex dimension 1. Okay, so how can we understand the condition? So what would be these manifolds? consider complex, no, consider 2k dimensional matrix. With a map. If we have manifold with a metric, it has holonomy. Holonomy of the metric preserves metric, so that's why it is inside SO.
Yeah, but even without metric, in principle, we can have holonomy in tangent bundle.
But there is a holonomy of what?
Of any connection. So any connection in tangent bundle will lie in GL,
Yes, but
GL
here,
to K.
but here I start with a manifold with a metric.
Yeah,
And
but
if I
I said
have-
that metric is not necessary condition to have holonomy. So on a manifold with a metric, you can demand that holonomy
Yes,
is
but
compatible with the metric.
you see, I am explaining it this way. So I start with a manifold with a metric. It has a holonomy. Holonomy means that from this we have a connection.
Levi-Civita connection.
Levi-Civita, yes. And this connection has holonomy. So since this connection preserves metric, it lies inside SO2K.
Excuse me, why we even dimension?
Let me study even dimension first of this one.
Yeah, but it is also true for arbitrary dimension.
Yes, but
So.
I would like to study even dimension. Now, suppose that manifold has covariantly constant spinor. What can show, and I will not show it, but in this case, holonomy is S U K. I am not going to show it. So since SUK lives inside UK, inside SO2K, we get the following. If holonomy is in UK, it would mean that metric is scalar. It is because in UK you preserve complex structure. I say it in one word. If it is SUK, it means that U1 component of holonomy is trivial. So what does it actually mean? What is the meaning of this U1 holonomy? You take top holomorphic top forms, and you restrict your holonomy on holomorphic top form. it means that here we have Kähler manifold with a single non-degenerate with a non-degenerate holomorphic top 4. You see, I'm skipping some details. I'm just trying to give you the ideas. And if you try to go into details, you know where to look into the literature. So such manifolds with holonomy in SUK are called Calabi-Yau manifolds.
You said you know if you look the details in general or a specific book, because I don't know the specific what's the best reference for context management.
You see, I also don't know. It's written in many places.
So like one possible reference is mirror symmetry book. So at least in introductory part, they kind of discuss like supersymmetry, Calabi-Yau, and so there is some introductory part with differential geometry. It is quite short, but it is sort of mostly focused on kind of giving introduction to Calabi-Yau and at least listing.
So for k equals to 1, you see, but I'm not talking about this. I just mentioned some facts. So for k equals to 1, the only thing that we have is two-dimensional torus. For k equals 2, there are two spaces. Four-dimensional torus and k3.
Are you sure that it's just billions? It's not like 10 to some huge number, 10 to the
Okay.
1000 or something.
Okay.
It's like thermodynamic number of this
Okay.
magnitude.
For me, it's enormous amount. And people like to study case k equals 3. But we are not so ambitious. We will study case k equals 2. So in this case, there is a single distinguished manifold called K3. There are two ways to look at it. One way. Consider T4. And this is C squared, and here we identify Z1, Z1 plus 1, Z1, Z1 plus tau 1, Z2, Z2 plus 1, Z2, Z2 plus tau 2. But this is four-dimensional torus. What would happen if we simultaneously identify Z1, Z2 with minus Z1, minus Z2? What is important is that holomorphic top form goes to itself. So the actual problem is that information. Has fixed points. In particular, let me draw these fixed points. 0, 0 is a fixed point. 0, 1/2 is a fixed point.
Oh,
So you can compute the number of these fixed points. So let me, for simplicity, take tau 1 equals tau 2 equals to 1. So fixed points are products of points on the first torus with the points on the second torus.
so 1 equal to 2 equal to 5.
Yes, right.
Would this identification make this thing non-orientable, or it doesn't have to?
So
No, no,
it is orientable.
This is just torus, but what if we blew it, what if we identify points with minus themselves?
It has nothing to do with orientation. Since this acts on complex coordinates, it preserves orientation.
This existence of complex coordinates always
Yes.
gives
So this actually means that points with coordinates x1, y1, x2, y2 goes to a point with coordinates minus x1, minus y1, minus x2, minus y2. So you have 4, not plus, but times 4. You have 16 fixed points. So what can we do? We would like to have a manifold. So people do the following. People blow up these points. And after they blow up, they take a closure. In real. So how to draw it? So if you know what blow up is, you'll probably understand. If you don't know what blow up is, you may understand it in the following way. In blow up in C square means that first you cut a point away, and then instead of the point, you put here CP1 of directions. To this point. So it is block. And then you can take a quotient. And as a result, you are getting an interesting manifold. In case we obtain this way, you get 16 new H2, 16 new elements of cohomology. Okay. So now let's try to see the dimension of the second cohomology of this space. Originally, we had the following differential form: dx, I'll call them dti dtj. So t is either x or y. So what was the number of this form? 4 times 3 over 2. So there were 6 of them. And you see that these differential forms are invariant under these two projections. So H2 of K3 equals 16 plus 6, it equals 22. It's one way to see this space. There is another way to see this space. Consider all quintities. In CP3. So I'm writing down the equation with homogeneous coordinates. Probably it's better to put here x1, x2, x3, x4, and write here something like a xi1, xi4.
That's the problem with the coordinate.
And in this way, you may compute the number of parameters. It is big enough. And parameters should be computed up to the action of GL4, because you can freely interchange generators. And in this way, you will get, again, 22.
Sorry, is this standard name? Why is the fourth degree?
Okay, why fourth degree?
Why is it called a quintic?
Quintic because of degree 4.
Quintus 5.
Quartic.
Quartic.
Okay, quartic. Now, how to see that it is a quartic? Actually, how to see that it's Calabi-Yau space? It is actually because one can construct a holomorphic top form here using the following construction. dx1, dx4, we put f in the denominator, we contract it with the Euler vector field, and we take a residue. Since we have the denominator, we have a residue. So this is a 4-4. After I contract with the Euler vector field, it becomes a 3-4. After I take a residue, it becomes a 2-4. So there are two ways to see this K3 manifold. I will call this topological, and I will call this algebraic. Okay.
So, what did you construct by this? What does this construction do?
This construction, a holomorphic top form, because here is 4, x1, x4.
Yeah.
I contract with the Euler vector field. It gives 3.
Yeah.
Then I take residue.
Ah,
It gives 2.
so it's a 2-0.
Yes, of course. Holomorphic, you see, when I say holomorphic, I always want to do.
Yeah, so in principle, there is a third method where you literally compute first Chern class for hypersurface of certain degree in CPM.
Yes, but instead of this computation, I gave explicit.
Yeah, but that's most common way. Like if you open the literature on kind of Calabi-Yau construction, they typically instead of giving explicit formula, they compute C1 and show that C1 contribution from CP3 is like 4, and that's why we need degree 4 hypersurface to cancel this 4.
But I think that if there is an explicit formula, it's better than existence theory.
Yeah, but that's kind of how literature works, unfortunately. No.
Okay, so I'm trying to give explicit formulas when that's possible. If there is an explicit formula, it's an explicit formula. So you may ask how this formula works for a topos. x1 cubed plus x2 cubed plus x3 cubed plus the x1, x2, x3 in CP2. It should be a torus. I write exactly the same formula. Here I have a holomorphic, non-degenerate one form. And this is a known statement that cubic in CP2 is a torus. So in this way, this quadratic is an example of Calabi-Yau, and there is also a famous example of Calabi-Yau in CP5. Sorry, in CP4. I add here S5, and I add here DS. And this is a famous wing.
Which presumably is depicted in the statues of Calabi-Yau which we see around the institute. So there is a rumor that this thing is actually like some kind of section of that thing.
Yes. However, I'm not going to describe the quintic at the moment. I'm going to discuss the quadric. Now, if it is a quadric, if it's a quartic, thank you, Slava, then we can study the following. We can study the lattice structure on its second cohomology. What does it mean? It means that you take one element, you multiply by another element, and you integrate over K3. And this is a pairing. H2 times H2 to real number. Given by this formula. So if there is a pairing,
A lower dimensional example would be that a structure on H1 of, say, a torus, where
Yes.
you integrate over the torus.
yes.
Mhm.
And in the lower dimensional example, on a torus, very good. We roughly speaking have dx and dy, and the pairing is dx dy is what? Is 1 minus 1, 0, 0. If I do it, so it is on a torus T2. Then we may compute it on a torus T4. I don't remember it by heart, but that is something. So all elements,
Just two copies of this. Then
No, H2 is 6 dimensional.
H2. It's not H2.
Yeah, so it is 6 dimensional, so it should be 6 by 6 dimensional.
so for each element, so it's a 6 by 6. So I think that it should be like this.
Because it's even dimensional form, it is.
Yes, it's an even dimensional
symmetric in
form.
this block.
Okay. So it's not that difficult.
The map is probably, is it to R or is it to C?
To R. You may even say that it is to Z.
To Z is some basis of basic elements of.
So how you do it? There is an integer basis in second homology.
Alright.
In second cohomology.
Cohomology is with integer coefficients.
Now, it's interesting to see what happens for K3 manifold. So for K3 manifold, the answer is like this. E8 times E8 times 3 forms of the type 0, 1, 1.
You need to specify like what do you mean by A, it's like Cartan matrix.
Yes. So what is E8? Suppose we have Lie algebra for E8. Then having a Lie algebra for E8, we have a metric on generators. And let us say that we take trace in a child. Oh, what I'm writing. Pair of two generators go to trace in a joint representation of T8. It's a killing metric. So it is a metric on Lie algebra. And the mathematical fact is that you may compute, that is, in K3, you may compute this metric on E8, and it turns out that it's a purely mathematical fact. I don't know how to reproduce it by hand waving. But let us believe in this fact. Okay? So one thing I already computed. 8 plus 8 plus 6 is 22.
Excuse me, H2, the lattice is 22 dimension,
Yes.
and it's related to H2, but why it's also related to this Lie algebra?
It is a mathematical fact. It turns out that
Because I still don't get, the first we get K3, can we use the same way to blow up just one T2?
so probably, but I don't know how to do it.
Blow up because now we only have 4 fixing points.
No, so
Using the same
you see, when we had the torus T4, it is the end of computation. So on K3, we have 16 fixed points,
Yeah.
and we have cohomology associated to each of these fixed points.
Yeah. Also, I don't understand why we can relate the H2 element to the 16 fixed point.
Because whenever we are doing a blow up, we grow up a sphere. So in the blow up, roughly speaking, you start with C square and you roughly speaking end up with C square and here is CP1 inside. So this is what happens if you just do the blow up.
Yeah, when I've seen blow up, but I understand it as a way to substitute variables instead.
Yes, it's exactly this. So when you say that you substitute variables, then you are, after you change variables, then you look at the new ring of functions. Or new field, it depends what approach are you using. And you see that the blown up thing is like this. You replace a point that you are blowing up by CP1. And when you are acting by this Z2 action, you take one point here, you go to another point. Directions are not invariant.
Yes, so previously, if you had like a small S2 around this point, you can just contract it to a point. Like this S2 was contractible, so it wasn't element of second homology. But now, because you preserve directions, now S2 is not contractible to a point. So that's why around each point you can draw S2, which is not contractible. So that gives you a generator in second homologies. And because of the duality between homologies and cohomologies, you can say that extra 16 generators for homologies around these points should give a rise to 16 representatives for second cohomology.
What would happen if we try to do the same for not the T4 but for T2? There we also have this, we can do this map and we have four fixed
You
points.
see, 42, we would not do it because dz goes to minus dz. So we have no chance to get a Calabi-Yau space. And also, in order to make a blow up, you need at least 2 complex dimensions. So blow up could be done in the complex codimension 2. And you see, up to these gaps, I explained the total number, that is 22. But I cannot explain how to get this lattice. At the same time, what I can explain what E8 is in classical terms. So I'll do it.
But this E8 times E must related to the 16 fixed points, right?
Yes.
Okay.
So let me try to explain you what E8 is as a Lie algebra, so that you will understand it. Not as some letter with some number. Motivation comes from the Dynkin diagram. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7. So this is a thinking diagram for E8 that you may read in the book. So, how to model E8 if you need it? You do the following. You add the maximal root to the diagram, and you cut one of the roots. In this way, you get a subalgebra. So it turns out that the maximum root is here. And what you cut is this. What you have here, 1, 2, 3, 4, 5, 6, 7, 8. You have here SO16. Now we need to model E8. So using this trick, we see that SO16 is inside E8. So what is left? What is left has a link to this node. So it is a spinner. I will call it spin. So I will say that E8 is actually SO16 plus spin 16. So what is the dimension of SO16? It is 16 times 15 over 2. It is 120. Now, what is the dimension of spin 16? So it is a self-conjugated thing, and this would be left spinner or right spinner, it doesn't matter. So it is 2 to the power 8 minus 1. It is 2 to the power 7, it is 1 to 8. So here we have 1 to 8. So totally, the dimension of E8 is 248. And you may look in the textbooks and see that actually the dimension of E8 is 248. But it's not only dimension that we are interested in. We are interested in multiplication table. But it's very easy to guess multiplication table. Multiplication table inside SO16 is clear. Then SO16 acts on spin using the Lorentz matrices. And spin 16 times spin 16 goes to SO16 using gamma matrix. So that's it. In this way, I kind of describe E8 in classical terms. Moreover, all groups like F, G, like E, F, G could be represented in this way. All groups, I mean all E algebra. It's something very simple. Okay. So now,
Yeah, but I think like one small correction, because killing form as you define it is defined on generator. Generator, the number you say 248. But this thing which is intersection, like 16 by 16, I think it's called like Cartan form.
Yes, I saw.
So it's not Killing form, it's Cartan.
Yes,
Because number of generators is
You are absolutely right.
too big, so it's on Cartan subalgebra.
It's Cartan. Thank you, Slava. Of course, it's
So
so.
among these generators, there are like 8 which are commuting, maximal commuting subalgebra is 8-dimensional.
Yes, and here it's clear. So if you would like to compute something here, it's clear. You just take 8 commuting rotations, and they will form
Cartan.
Cartan subalgebra. Okay, but this was mathematics. Now, let us kind of go back to physics. Namely, let us try to study 11-dimensional supergravity compactified on K3. By the way, if you'd like to read more about K3, there is a book written by Aspinwall, who is a mathematical physicist, called K3. So all you would like to know about K3 is in this book. And now consider M5 ray wrapped over K3. So what would we have? I forgot to say one thing. That if we have second cohomology, we have actually 2 structures. One structure is a metric that I described, but there is another structure. This another structure is the star operation. Actually, star of omega is also actually, if omega is a harmonic representative of a class, then star omega is also harmonic. So we have a Z2 operation. On H2. So there are self-dual forms and anti-self-dual forms. And it turns out, I'm sorry, I erased it. It turns out that these are self-dual, and here forms of this type are also self-dual, and forms of this type are anti-self-dual. Okay, I forgot to say. Now M5 brain is wrapped over K3. And let me take a B field. B2, it is a self-dual to form on M5 brain. And then I wrap it over K3. And then I decompose B as follows. Omega self-dual I field phi I plus omega anti-self-dual alpha field phi alpha. So from this I see that after compactification, I am having a one brain. I am having a one brain. And on this one brain, there are 16 plus 3 self-dual scalar and 3 anti-self-dual. So what does this mean? It actually means what self-duality of a scalar means. Scalar is self-dual if it is holomorphic. So I have 16 plus 3 phi i's with equation of motion d bar phi I equal to 0. And 3 phi i's with equation of motion d phi I equal to 0. This is a self-duality equation in 2 dimensions. Okay, if you are surprised, let me try to write it like this. Consider d phi. What is self-dual? So actually, I need to put I here. So when I'm studying self-duality, there is the following phenomena. That star square is not 1, sometimes it would be minus 1. That's why in dimension 2, star square is minus 1. So self-dual means this. So let us write it down in components. Now self-duality is acting on dx, it is dy, minus dx d phi over dy. But this is exactly so in front of dx I have, or in front of dy. In particular, I have dy, and here I have d phi over dy minus I d phi over dx. So it is Cauchy condition. It is a holomorphism. So self-duality in real dimension 2 is holomorphism. So anti-self-duality is anti-holomorphism. So that's why I have exactly (16 plus 3) left mover and 3 right mover. Now, all this was about a string. But string can move in R7. The motion of string in R7 gives me produces 7 left movers plus 7 right movers. So altogether, we have 16 plus 3 plus 7. It is 26 left movers and 3 plus 7 equals 10 right movers. But it is exactly what people used to call heterotic string. It's a string where left movers, in which it's a string where there was 26, and it's a critical number for bosonic string. Left movers and 10 right movers. So it is heterotic string. So now the question is, okay, if this is a heterotic string, what is its target? So I am not going to explain this in detail, But the target target of heterotic string is the following. So what is the concept of the target? Where momentum, where left momentum and right momentum so left momentum lead in self-dual part of the lattice. And right momentum lead on, I call here this self-dual anti-self-dual process. Now, what is important? If momentum live in the lattice, I have very special vertex operators. So, to understand my last comment, you need to know a little bit about string theory. So it's not for everybody. There are vertex operators of this type, where phi is a left moving scalar. So if you studied chiral algebras, you know this. Well, let me call it VP. And then, if dimension of VP is 1, they form a current algebra. VP1 of Z, VP2 of 0, and actually you can compute this app.
Is there a level of this current algebra? Or
So I would like to say that this VP and the operator of this type form a current algebra. The simplest example of this current algebra is I equals to 1. E to the I phi, e to the left, e to the minus I phi left, and d phi left. And they form SU2. So probably you know it. This has a generalization. If P left I are roots of a lattice corresponding to the other. In particular, in the example that I am describing, these P's so in the case that I am describing, in this case, you will get E8 in this way. You will get E8 times E8 times U1 left cube times U1 right to cube. Okay, left out. Everything is made of the chiral bosons that we are getting after compactification. So please follow the line of wisdom. We started with the M5 brain. It had a self-dual 2 form. We compactified on K3. We got some number of, we got 19 chiral bosons or self-dual and 3 anti-chiral bosons. And now, using these bosons, we can construct vertex operators of corresponding string theory, and that is exactly heterotic string theory with the gauge group E8 times E8. So that's how it goes. So I omitted some details, but I kind of completed the duality pentagon. So in duality pentagon, the question was, how can you ever get? So 1, 2, 3, 4, 5. I don't. So people used to write this stuff. So the issue was, how can you get, in a natural way, heterotic string using supergravity compactification? And the simplest answer is that you can get it if you compactify supergravity on K3. So you see what is interesting, that under dualities and under compactifications, all extended objects go into each other. D branes can grow in dimensionality under T duality. Now, D brane could be interchanged with a string. And even heterotic string could be obtained from M theory fiber. So I would like to conclude it by saying that duality business is not a science. We apply group of dualities that are T dualities, S dualities in different order. And we are getting relation between different objects. So it is a set of tricks. And still we do not have a formulation that explains why it works. But people consider it as granted. It works and it is never broken. And if it works, people think that if it works, let us take it like this. So it's more severe than what people were doing in normalization and quantum field theory, where people say, shut up and calculate, it works. Here we are just applying strange looking axioms, and they are self-consistent. And we don't have a fundamental understanding. What does it mean? It means that we are studying symmetries of something. But what is this thing? What is this something? We just don't know. So this concludes my set of lectures on M theory, and then Tamoki would tell you more about a theory on M2 branes and related conjecture. Okay? And I know you also have a course on physics on brains. So it's another point of view on the same subject. So you see, I was able to get you 26. So I honestly computed 26, and
As a 10 plus 16.
as a 10 plus 16. No, yes, as a 10 plus 16, yes. And I explained that 16 are the extra second cohomology of K3. and I gave you the idea how to get current algebra. So you'll get vertex operators that correspond to currents of E8 times E8. So that's it.
So, am I right that so the conformal dimension of these vertex operators depends on the length of this PL?
Yes. So as PL you are taking roots.
Yeah, but for some, the algebras, all roots have the same length. But there are the algebras where they have different length, right?
Yes, but
And in that case-
but in this case all roots are.
Yeah,
of
yeah,
the
in this
same.
case I get it, but what happens if we take the algebra with roots of different things, and they would not form a current algebra, they would form some other structure, maybe, or it's not physically interesting?
I think it is possible to do it because you see,
And the
no,
examples are-
low roots. Okay, so I understand it for the case where roots are of the same length. If roots are longer, they don't form a current algebra. So they would form a field of dimension 2. And the question is what you are going to do with these fields. The operator products of these fields would not give you what you wanted. Okay, maybe I'll try to explain it in this way. So this has dimension 1, dimension 1, and dimension 1. And in operator product, you will have 1 over z and the structure constant of SU2. You can take e to the 2I from here. This would have dimension 4. And if you consider operator product of this with something here, you will get higher order poles. Moreover, having this operator of dimension 4, you will not be able to make a vertex operator in string theory. Because vertex operators in string theory say it bosonic string theory are C times V in terms of field. So here you want dimension 1 because C has dimension minus. So if you study this object, you will never be able to construct a field of dimension 0. So it will not be in the Q cohomology, so it's not reasonable to study it at all. At the same time, if you have fields that are holomorphic and have dimension 1, then you inevitably have this structure VA, VB of 0. And this is inevitably, this inevitably has has the structure of the algebra structure courses. You may check it. The if operator expansion goes like this plus a. So it means that if you have consistent left movers, like here, you inevitably will get Lie algebra. So when I say consistent left movers, I mean case where left movers are kind of decoupled from right movers. If they are pure left movers. Okay, so it's an answer on how they are related, but you see it needs some knowledge in conformal field theory and in string theory. So that's it. I think it's good enough for introduction. You know, you probably know the basic points, and you can look for detail if you are interested in it. And one thing, don't think that someone would explain you the fundamental structure in the deeper way. If you will go to books, you will see a lot of examples and applications. What if we use not K3? What if we use Calabi-Yau? What if we use specific Calabi-Yau? What if we go to some limit in Calabi-Yau? What would happen if you study non-compact Calabi-Yau? What if we wrap M5 brane over a curve inside some other Calabi-Yau? You see, that's what people are studying. But I gave you the concept. So I was teaching you the main concepts of the main players of this game. Okay? So if you are interested, you will see how these players are playing different games. So I thought that your education was incomplete without this knowledge, or would be incomplete without this knowledge.